Well, what you just saw was the vertical takeoff of an F-35, and that was my main interest on this project, is that how this plane can go to high temperatures and without melting, because on that takeoff we didn't see any melting, even though it was going at pretty high temperature. Also, when it goes to the highest speed, the plane can go over 1,000 of Celsius, but we don't see any melting happening on the plane, any scratches, any damage. So then that leads us to the turbine, more specifically the Pratt & Whitney F135 turbine. Then, well, as a simple and brief explanation, it is a turbofan jet engine with an afterburner, and the materials that we're gonna focus today is the titanium alloy. You're gonna see that it's pretty mixed with aluminum to make it more strong. So yeah, this is the decision, this is the topic that I'm gonna focus on. And if we see at the table content, it has a pretty high content of titanium, obviously, and the other highest that it had is the aluminum. Based on research, the aluminum is for just to make it stronger. Even though it melts at a lower temperature, it adds mechanical properties to the titanium. And yep, I want to show the periodic table of the titanium and aluminum since they are the highest one. So right here, what I like to focus on is that the electronegativity, they are pretty close to each other, but the melting point, you can see like the titanium is 1,000 above the aluminum, and pretty high temperature. So that helps. That makes sense. Like, oh, we wanna make a turbine with these material properties because we don't want it to melt. Now the chemical bonds. So it is a metallic bonding. So that means that it's gonna have a free electron mobility, and then this also means that it allows to be ductile material, pretty high conductive material, and adds to toughness. Now, if we go pretty small and we see the micro structure, we can see that after the plastic deformation, it is a pretty solid alpha phase, meaning that it is a pretty solid titanium phase, and the shape or the face represent an hexagonal closed package HCP, like I mentioned before, and it has the most of it is titanium based, but the aluminum and the tin each offer some strength, just make it stronger. And yep. Then on the defects, we're gonna go kinda brief because there are a lot of them. So on the point defect, we can see how we have substitutional atoms. That is the other ones that they are replacing the titanium, and the vacancy, some missing spaces, and the interstitial. I always have trouble with this word. Atoms, that which is the oxygen, nitrogen, hydrogen, and carbon. So it's just like they sit in between pretty small places. So then the line defects, so movement and dislocation, they are harder. Then the alloy has a higher strength, and dislocation density increase with cold work. And for last, the surface defects that I would like to talk about is that the grain size, it does affect the fatigue, and then the deformation, it appears under high strain at low temperature. So as we saw before, here dislocation density increased with cold working, and now here low temperature that tells me like maybe we shouldn't work with this material with low temperature. On the mechanical properties, I would like to focus on the elongation break. So that just tells us about the limit, the range that we can work without breaking. Pretty good, 18%. Then here I would like to talk about the tensile modulus, which is used for different aerospace applications, such as the turbine, the rotational force, etc. I don't really wanna go deep into it, but it is a pretty important one. And then the fatigue strength, that the fatigue is what we already know how much is the lifespan of this material. Okay, so now we go to thermal properties. It just tell us about the thermal expansion, how on different temperatures, how much the material is gonna expand. Like maybe we want it to expand, but we don't want it to expand that much. Then the melting point, huge. And these airplanes, they run a pretty high temperature, so we don't want it to melt. Thermal conductivity is telling us about the thermal properties, about and how tough it is. It has different uses, and then a specific heat, it just tells us how fast the temperature will change. For manufacturing, I would like to focus on this melting, forging, heat treatment, and welding. So on the melting process, the name of the material at the end, I don't know if you remember, it has that titanium, and then at the end it has this ELI. Well, that means extra low interstitials. Pretty difficult word. And yeah, just mean like it's a pretty detailed, careful process. We don't want oxygen. Oh, we don't want to have a lot of oxygen, nitrogen, and hydrogen. And then for our forging process, I would like to mention that it runs at pretty high temperature, as you can tell, almost 1000 Celsius, and it's usually finished before the beta phase. And the heat treatment, and so I like to say that the stress release, we lower the temperature, we let it run for 4 hours, and then the annealing, we put it back in, and we increase the temperature a little bit for half of the time. And on the welding process, and we do some electron beam, laser welding, and just for a fact, alpha titanium, it usually welds better than the alpha plus beta or beta alloys. And to finish with this topic, I would like to mention some applications. So we saw it before, materials that they run at high temperature, so airplanes. And here, yeah, I have aircraft, spacecraft, and this is the turbine of the F-35. We saw it before, this is a big turbine of the Boeing 777. This is the Blackbird, one of the fastest planes that we ever built, and of course it's gonna run at pretty high temperature. And then this is a part from the Apollo 11, and you can see this guy, how huge this is. You can see the guy right here standing, NASA. So yeah, you can see the relationships of using these titanium materials that we use for huge parts. I haven't seen it for a phone, or I haven't seen it for a small circuit, so we usually see it on space machining or aircraft machining, and yeah, they run a pretty high temperature. Also, I would strongly recommend watching both of these videos. I think they help me pretty much to understand how this process works and why do we need those materials. So you can look it up. You see the title name right here, both of them. So this one talks about some chemical properties, and it talks more about the material itself, and this one down here talks about the manufacture process of the turbine of the F-35. So both are pretty useful, and I recommend them a lot.